which really just means we want to understand how do lines and graphs, how do two lines on a graph behave with one another. And we saw that there's three different scenarios. Either you have two lines that cross one point, you have two lines that never intersect and therefore their slopes are the same, which means that they're parallel lines. Or you have this scenario where you have an infinitely many number of solutions, which just means that there's one line on top of itself. And we studied how to solve a system of equations by graphing it. So we literally graphed two lines and saw where we intersected, where they intersected, and those coordinates represented the x and y values that would make our equations true, and therefore they're called solutions. So now we're going to do another method. We're going to solve using what's called substitution method. So today we're going to learn about the substitution method and the elimination method. So these are algebraic methods. And what we mean by algebraic is that we're just using numbers and variables. We're not going to be using a graph anymore, because it can get a bit tricky if we try to graph every single line and try to solve it that way. It becomes very difficult when the points of intersection are not on, like when the x and y values are not whole numbers, when they become fractions, or they could even be they could be irrational numbers. So then that's when things get a little bit complicated. And so we're going to be studying how to do this without having to graph anything. So I'll give you the first example. Let's say I have a system that looks like this: x minus 1, y equals x minus 1, and 2x plus y equals 5. So this is my first equation. This is my second equation. Now, this is a system of equations. Why is the system of equations? Because I have the first equation being a line, and I have the second equation being a line. And I want to solve it, right? I want to solve. So I want to solve system, solve the system. And what does it mean to solve the system? I want to find what x equals, and I want to find what y equals. I want to find what they equal so that the two equations are true. So what's the first thing we do? Well, if you notice, in the first equation, y is already solved for. So we're going to take equation 1. You take equation 1 and plug in expression yeah, there we go, Tyler. Yeah, we isolate the y for the second, but I think it's easier just to do the first equation, right? So plug in expression for y in equation in equation 2. Okay, so then what is that going to look like? So this is going to be 2x plus, and now instead of writing y again, well, I'm just going to write it just to show you that now I'm going to replace, I'm going to substitute in the y value, substitute with the expression 2x plus, this becomes now x minus 1 equals 5. So do you guys see that? I'm just going to substitute in now. And that's the first step. And then the second step, so once I have this, I can solve for x. Now I have an equation, 2x plus x minus 1 equals 5. What's nice about this now is that this equation has only one variable in it and not two. And so now I can solve this. I can first combine like terms. I get 3x minus 1 equals 5. I can add by 1 on both sides. So I get 3x equals 6 divide by 3, and I get that x equals 2. So x equals 2 is one of the solutions. Now I need to find the y value. So step 3. To find a y value, I'm going to plug in x equals 2 into either equation, equation 1 or equation 2. So I should say plug in x value found in step 2 into either equation 1 or equation 2 and solve for y. So that's what we're going to do. So look at the two equations. We got y equals x minus 1 and 2x plus y equals 5. So I can choose either equation. It shouldn't matter. But the first equation looks a lot simpler than the second equation. So I'm going to say use equation 2. And I'm going to say this is y equals, what is it, x minus 1. But then what's my x value? It's 2. So I'm plugging it in. And I get 1. So what do I get? I get y equals 1. Right? So then what's the solution to the system? What's my solution? My solution is the coordinates 2, 1, or x equals 2 and y equals 1. Right? So what we did was we solved this equation with we solved this system without having to graph anything. We used just algebra. We found x first by substituting everything, the y expression in the second equation in terms of x, and then we solved the equation for x. And once we got the x value, we plugged it in to the equation number 1, and we figured out the y value. Now, to do the whole job completely, we have to check whether or not what we found is correct. So does x equal 2, is x equal 2 and y equal 1 really a solution? Or the solution, because it's the only one solution? Is x equals 2, y equals the solution? So then check. What's the first equation? The first equation is y equals 2x minus y equals x minus 1, which we already did, right? We got that 1 is equal to 2 minus 1. 1 equals 1. Check. So this is equation 1. Now look at equation 2. What does equation 2 say? 2x plus y equals 5. 2x plus y equals 5. Is this true? If I plug in the values? So 2 times 2 plus 1 equals 5. 4 plus 1 equals 5. Definitely equals 5. So check. So indeed, yes. Yes. It is the solution because it makes both the equations true simultaneously. So any questions about this? Is this clear, the substitution method? Yes, crystal clear. Okay, great. I'm glad. Okay, good. So now let's look at another example. Now, what if I get 3x plus y equals 2 and 2x plus 3y equals negative 8? These are my two equations. I want to solve. I want to solve the system. So what am I going to do? Now, what's the difference between this example and the previous example? The previous example, one of the variables, which was y, was already in terms of x, meaning that y equaled some expression with x. The problem here is that I have the x and the y's on one side of the equation, on the same side, and they're both in standard form. So it's not clear as to what one variable is in terms of the other. So that's what we have to do. So step one here, in this case, I have to solve for one of the variables for one of the equations. So solve for one of the variables using either equation. So the reason why I write it like this is because you have the choice. You can say, hey, I want to solve for x, or hey, I want to solve for y, and hey, I want to use equation 1, or hey, I want to use equation 2. The thing is, we don't want to complicate our lives, right? We want to simplify them. So there's going to be, most of the time, there's going to be one way in which it's better or more convenient or easier to do than the other. So for example, in this case, what is it easier to solve for? Is it easier to solve for x, or is it easier to solve for y? And based upon that answer will be based upon what equation do you use. Do you use equation 1 or do you use equation 2? So that's something you have to kind of see it for yourself. And so Jalen, you say y. Why do you say y? What makes y easier? Because in equation 1, y, so if I use equation 1, it's easier because y is there's only one y. That's right. And so to get y by itself or isolated, I only have to do one step. I literally only have to subtract 3x on both sides. So y equals negative 3x plus 2. If I would have to solve for y here, the problem with this is that I'll subtract by 2x. That's no problem. It's just that I have to divide by 3. And then that expression has to be plugged in here. So that's too much stuff, too many fractions. I don't want too much problems. I don't want any problems. So then I got it. So y equals negative 3x plus 2. Okay, so now that I have that, I figured that out from equation 1. Now from equation 1, I need to now plug in or substitute. I think I like substitute better. Substitute expression found in step 1 into other equation not used. Not used yet. So which equation did we not use yet? Equation number 2. So we got equation 2. And what is equation 2? It's 2x plus 3, and I'm going to put y. I'm going to color this with y to indicate that this is the variable that I'm going to substitute in for. I'm going to say, hey, take this guy and just replace it. Replace it with negative 3x plus 2. So this will be 2x plus 3 multiplied by, and this is negative 3x plus 2 equals negative 8. And what's so nice about this is that now I have an equation with only one variable in it. That's the whole point behind this substitution process. It's the whole point of it. So step 3 now, solve for x. So now we have what? We got 2x, and then I can distribute the 3, right? I can distribute the 3, and I get minus 9x plus 6 equals negative 8. Negative 7x plus 6 equals negative 8. Negative 6, negative 6. Negative 7x equals negative 14. Divide by negative 7. And I get that x is equal to 2. Is it the same thing again? I got x equals to 2 here. Okay, good. So x equals 2. And now I got x equals 2, but now I want to figure out what y equals. So solve for x, and then we're going to do what? Plug in value found in step 3 into one of the original equations to solve for other variable. So we know what x equals. So we know what x equals. Sorry about that, Maria. I just had to unmute everybody. Okay, so once I found what x equals, now I can find what y equals. And I can use either equation 1 or equation 2. It seems as though equation 1 might be easier because y again is by itself. So then I'm going to use equation 1. And I get 3 times 2 plus y equals 2. 3 times 2 is 6 plus y equals 2. Then what does y equal when you solve for 6 plus y equals 2? When you solve for y, subtract by 6, you get that y is equal to negative 6. So y equals negative 6. And then what's my solution? My solution is 2 comma negative 6. Or I can write x equals 2, y equals negative 6. And of course we can check, and when we check it out, right, it works for both equations. Negative 4. Thank you. You see, you guys are on top. You guys, too good. Too good. That's right. 2 minus 6 is not negative 6. 2 minus 6 is negative 4. Correct. Thank you. Thank you. You guys are paying attention, which is awesome. All righty. So any questions about this? Is it straightforward? Do we understand like the technique now? We are solving for one variable. It could be x, it could be y. Once we do that, we plug it into the other equation, solve that equation with one variable. Whatever that variable is, plug it into the other equation, and we get the two values for x and y, and we're done. Okay? All right. If no other questions, let's see what happens when I get something like this. 3x minus y equals 8, and y equals 3x minus 2. So then we understand, right? Solve by substitution. So if I want to solve by substitution, it kind of seems simple, right? What we're going to do here? Well, y in the second equation is already solved for it. It's already by itself. It's already isolated. So I'm going to use equation 2 into equation 1. So I'm going to use equation 1. I'm not going to write the steps anymore because we already wrote that above. So I'm going to use equation 1, and I'm going to say 3x minus, now this will be parentheses 3x minus 2, and this equals 8. Distribute that negative 1, and I get 3x minus 3x plus 2 equals 8. But what happens? And I think, Emil, you're already understanding something here, right? 2 equals 8? No. This is impossible. 2 does not equal 8. So then what does this mean? This means that in our pursuits to solve the system, something breaks down. We get something that's incorrect. We get an incorrect statement, a completely false statement, erroneous statement. So therefore, it must mean, so since we get something that does not make sense, we say no solution. And if we have no solution, what does that mean about the lines? Remember, if you have no solution, no point of intersection, that means that the lines are. What's the only scenario where you have two lines that never intersect? They're parallel. So no solution, that means 0 points of intersection. 0 points of intersection between two lines means lines are parallel. If lines are parallel, what does that mean? Lines have same slope. So all these mean the same thing. No solution, 0 points intersection, lines that are parallel, same slope. Okay? So you can have scenarios where the substitution method doesn't mean that it doesn't work. It's working perfectly. It's just that the very structure behind this system is no solution. And this is called remember the word for this is called inconsistent. This is an inconsistent system because it has no solution. Okay, so any questions about having no solution? It can happen. Things like this happen all the time. Okay. All right. Now I'm going to give you another example. Now, what if I have a system where it's 4x minus 2y equals 6, and I got y is equal to 2x minus 3. So again, solve by substitution. By the substitution method. So then what is this going to be? 4x minus 2. And we'll replace this by 2x minus 3. Why is that? Well, the y value here is already solved for again. So I just plug it in. And when I plug it in, what happens? Distribute, and I get 4x minus 4x plus 6 equals 6. Okay, so I get this thing. What happens here? The x's cancel again, but what happens this time? I get a true statement. 6 does equal 6, but I don't get what x is, and I don't get what y is. So then, what would be the conclusion to this? Remember, there's only 3 scenarios. You have 1 solution, you have 0 solutions, or you have infinitely many. That's right. So the conclusion is whenever we get a true statement, then we have an infinitely many, and there's no x values or y values, there are infinitely many solutions. There are infinitely many. And what are they? And this is called a dependent system. And what are those solutions? How do we write the solutions? So one way to write them, solutions, is we're going to write them in a general sense. So we're going to write them as coordinates, x comma. Normally we would say y, wouldn't we? X comma y. But we're going to write y in terms of x. And it just so happens that y is written already in terms of x. So if I write y, I can also write 2x minus 3. This is my solution. This is one way to write it. X comma 2x minus 3. So for every x value that I get, as long as you plug it into this form, that's going to be your y value, and those two x and y values are going to make this system true. Okay. So now we saw all scenarios. We saw 1 solution, we saw 0 solutions, and we saw infinitely many solutions using the substitution method. Emil, yes, please ask.
Yeah, so you said, wait, so how'd you get to the solutions x comma 2x minus 3? Like, how'd you do that?
Right, so it's just a way to express what the solutions are. So if I say, okay, I'm solving a system of equations, and I found that in my procedure, I get a true statement where all the variables disappear. So which means the conclusion is that it must be infinitely many solutions. Now the question is, how do I express the idea of infinitely many solutions? First of all, I'm a finite human being with finite time. I don't have time to say, hey, these are all the number of solutions. But what I could do is I could express it in a general sense. And how do I express it as a general idea? I use variables. So then I'm going to say the solutions are of the following form. for every x value that you plug in, whichever one you choose, I don't care what x value you choose, what number you choose on the number line, the y value must be 2x minus 3. Why is that? Because as David mentioned, and as we see, the y value here, right, the y is equal to 2x minus 3, meaning that the y coordinate, whatever that is, has to be twice the x coordinate minus 3. Just by writing this down, I have written an infinite number of solutions. Why did I write an infinite number of solutions if I only wrote two little things here? The idea is that replace x with any number, I got the y value immediately. So in a sense, I got all of them. Does that make sense? And dependent solution, the dependent system means they're the same line. Two of the same lines. These are the same. This is exactly this. If you were to solve for y, you get this same thing. They're the same. So in a sense, you're just rewriting the line. That's what you're doing. You're just saying x and then the y value is the line itself, y equals 2x minus 3. It's a bit, it sounds like it's a bit redundant. It sounds like it's unnecessary to do, but this is how we express the solutions for infinitely many solutions.
All right, thank you.
Okay, good. Any other questions? Good question. No, great. All right. So if we understood the substitution method and you realize, oh, wow, it's not that bad, right? We're actually going to now learn another method called the addition or elimination method. Now, why are we learning so many methods, you may ask? Well, the substitution method sometimes is convenient and other times it is not. There will be situations where solving for one variable actually is not as easy. The examples that I gave are very nice, clear, clean, small numbers. But what if you have numbers like decimals? What if you have fractions? How are you going to solve for one variable when you have all these fractions there? That's when things get worrisome and they get annoying if you try to use a substitution method, unless you like doing that stuff, which it could be the case. But the addition method and the elimination method is the more, I would say, recommended way. And especially, remember we talked about having like 3 equations and 3 unknowns and then so on and so forth. When you talk about those kind of systems, we usually apply this addition method in a more general sense. So what is this method? Okay, so let's see this. So again, I'm going to be dealing with lines again, system of equations, right? I want to solve using the system of the addition method here. Pardon me. Now, if we were to use the substitution method, right, we would solve for x or we would solve for y, which we could do. We could do that, no problem, because the numbers here aren't that bad. But if you notice and be a little more perceptive, you start to realize, wait a minute, in both of these equations, I have this y here, but they're opposite sign. They're opposites. And it works out perfectly that, wait a minute, both of them have a coefficient of -1, right? And +1. So what do you think we could do? What do you think would be the reasonable thing here to do? Cross out the y's. That's right. But how do we cross out the y's? We have to add. We have to add both of the equations. And what's so nice about that is when you do that, -y plus +y, 0y. And like you said, Tyler, what's left is 4x on the left side of the equation and 16, pardon me. For some reason, I have I'm confusing my 6s and 4s. 16. 10 plus 6 is 16. Now look what I have. An equation that I can easily solve. And I get that x equals 4. Wow. That was pretty swift and easy and painless. X equals 4. Now that I know that x equals 4, now what could I do? Choose either the first equation or the second equation, plug in x, and then solve for y. I can use either equation 1 or equation 2. Equation 1 just seems a lot easier to use. So then I'm going to say x minus y equals 6. So that means that 4 minus y equals 6. Subtract by 4, subtract by 4. And I get that negative y equals positive 2. Which means that if I divide by negative 1, I get that y equals negative 2. So then what's my solution? My solution is 4 comma negative 2. You see that?
Professor,
David.
in the exam, are you gonna ask us to do, like, for example, like maybe you're gonna say us in the doing addition method or doing this method? Are you gonna say like that?
I think David asked the same question. Am I going to ask? Personally, I don't think I'm gonna ask. I'm just gonna ask you to solve. So it's gonna be up to you to decide, you know what, the graphing method. I am gonna distinguish though between graphing and algebraic. So if, for example, I say solve the system of equations using the graphing method, then it will be explicitly, I'll give you a graph and you'll have to draw both. But if you just have a random system of equations and you want to solve it, and I just say solve, which most likely that's what's going to happen, then you can have either 3 options. You can either graph them, you can use substitution method or the elimination method. But there's going to be one that's going to be more convenient to use than the other 2. That's really what you will have to be, you'll decide for yourself, I guess, which one would be more convenient to use. So that's what's going to happen.
Okay, thank you.
Mm-hmm. So for example here, I could have used both easily, no problem. And you would still get the same. You would get the same answer. But like I said, there are going to be situations where the addition method is actually preferable over the substitution method. So I'll give you another example. Let's see. Okay, yeah, I'll give you an example where yeah, I'll give you an example here. So this is 2x plus y equals 3 and x plus y equals 0. So yeah, this example is no good because I want to show you an example where the substitution method seems to be not as useful. Yeah, so I'll give you something like this now. So what if I get something like this? 8x minus 3y equals 21 and 4x plus 5y equals negative 9. So look at this system here. Would you try to solve by substitution? Meaning that would you select one of the variables to solve for and then substitute in that expression? That's going to get crazy really quick unless you really enjoy doing that and enjoy dealing with fractions all the time. Be my guest, but I would not suggest using the substitution method for this example. The elimination method is probably the best way, the most efficient way to solve. So then how do we approach this? The problem is that the first system, right, the first equation, it was very easy in a way because why? The variables, when you match them up, right, the coefficients were just opposite sign. They cancel out beautifully. The problem is that's not the case here. You have 8s, you have 4 for x's, you got -3, and you got +5. Okay, so then we have to do a bit more groundwork than in the previous example. So what's the first step? The first step is decide which variable to eliminate. If you don't know, you can literally flip a coin and then say, hey, I want X or I want Y. At the end of the day, it does not matter. But you have to make the decision first. So anybody out there, what would you want to simplify or what would you want to eliminate? The X or the Y first? The X. Okay, so I made the decision. I want to eliminate X. Now, the second thing I have to do, step 2, is I have to be perceptive and find the LCM of the coefficients of the variable chosen in step number 2. Step number 1. So what are the coefficients? 8 and 4, right? Can you just put a negative sign for everything on the bottom except for 9 because it becomes positive? Sure, yes. That's where we're going to get to. That's the idea. But if you just do that, Jalen, and then you try to add, you're not going to eliminate anything. Nothing would be eliminated. Right, Shazab. We're gonna do that eventually. But before we do that though, I want to make sure we see the steps. So I want to find what? I want to find the LCM. The LCM between what? 8 and 4. What is the least common multiple between 8 and 4? It's gonna be 8. Now the question is, why did I find the LCM? Who cares about the LCM? Well, it's related to the comment that was just made. You have to multiply by -2. But how did you know, Shazab, that you had to multiply by -2? Like, how did you know?
Well, I just knew that if you're doing it for x, that they have to cancel out. So I knew that we'd have to do 1 by a negative, and I just know that 4 times 2 is 8. So I just did it by -2 to get
So
the
very
negative
good.
8.
So very good. So the numbers here were indicated to you. They were telling you. They're like saying, hey, this number, just make this multiply this by 2 and you get an 8. And if you multiply by -2, you get a -8. And so there the 8s here would cancel out perfectly, which is nice. Sometimes though, these numbers aren't as telling. So that's the whole idea of the LCM. This is for like the general case. So the general case is the LCM. Now, what do we care about the LCM? Why do we care? Because now we can make both of those variables, the numbers in front of them, we can make it into the LCM. So then we say, hey, multiply each equation by the appropriate factor to make coefficients into the LCM. The thing is, however, 8 is already the LCM, so I don't have to do anything to the first equation. I can just leave it. I can leave it alone. That's why we don't touch it. However, the second equation, the 4 here, I have to multiply it by a 2 to make it into an 8. But not just that. I have to multiply by a -2. Now, why do I multiply the entire thing by a -2? Because I want to make them opposite signs. So I'm going to have to say this with opposite signs. So I have to multiply by -2. And when I do that, this system here becomes 8x minus 3y equals 21. Leave that alone. Distribute the -2. I get -8x plus, minus 10y equals +18. And now what can I do? Now what did I just achieve? I got a positive 8x in the first equation, and I got a negative 8x on the second equation. So I can wonderfully do what? I can add. I can perform the addition step. And when I perform the addition step, what's the step that occurs right after? I eliminate the x's. So the x's are eliminated. And then what's left? So step number 4 is add equations to eliminate the variable. So now what do I have? I got negative 3y minus 10y is negative 13y equals 21 plus 18 is 39. Divide by negative 13, divide by negative 13. And I get that y is equal to negative 3. Boom. I got y equals negative 3. So then step 5 would be solve for the variable. So add equations to eliminate variable and solve. And then once I have that, step 5, find value of other variable by substituting the value found in step 4 into one of the original equations. So what are the original equations? 8x minus 3y. I guess I'll just use the first one. So I get 8x minus 3y equals 21. So 8x minus 3 times negative 3 equals 21. 8x plus 9 equals 21. Subtract by 9. I get that 8x equals 12. Divide by 8, divide by 8. And what do I get? I get x equals 12 over 8. And if you reduce this, you get divided by 4, you get 3 halves. So x equals 3 halves. So then what's my solution?
0 over 2, comma, negative 3.
Perfect. That's it. That's it. So this is an example for which demonstrates why we would use the addition method and why the addition method in a way is superior than the substitution method, because it can it's much better to use in general. And Tyler, is it okay to make 3 halves into 1.5? Obviously, it's perfectly fine because they represent the same value. I'm just more comfortable, I guess, with writing things in fractions rather than decimals. So 1.5 would be okay. For example, if it was the other way around, though, if it was x equals 2/3, I would not write this as a decimal because the decimal here would be repeated. It would be 0.6 repeated. So it would make more sense in this example, in this case, right? If that's were the case, it would make more sense to leave it as a fraction because it's an exact form. You could put it this way as well, but it's just a little strange to write it as a repeated decimal. But yeah, for this case, you can write it as 1.5. No problems with that. Okay. Okay, great. Great. Cool. Cool, right? Okay, so now you're saying, okay, great. We know how to solve equations. We know how to solve using the graphing method and all of that, right? Now, why do I care about this, right? Maybe that's your question. What makes this so special? Like, why do we even? Is it just because it's Math 115, and they're telling me I have to learn how to do this, and there's no reason. There's no other reason why. It's just an academic task. Well, the thing is, no. The thing is, this kind of problem occurs a lot in our lives, actually. So I'll give you an example of that. So these are like applications, right? Applications of systems of equations. So the moment you may hear applications, some people may think word problems. Yes, that's another way to think about it, word problems, but I like thinking about it as applications. Okay, so I'm gonna write a scenario. At QC's coffee shop. I haven't been on the campus in years, so I mean, in almost a year, so I don't know if there's a coffee shop still there. So at QC's coffee shop, muffins cost $2 each, and lattes. People drink lattes still. Lattes cost $3 each. Okay, it's just a make believe place. If a total of 7 items were purchased for $18 altogether, how many of each item were sold? Now you may be looking at me like I'm strange because you're like, wait a minute, what does this have to do with system of equations? Does anybody see how systems of equations are applicable here? Yes. Okay, David, how? You can make a system.
Yeah, so X would be like the muffins, and then Y could be like the lattes.
Right. So then look what we're able to do. We're able to first, step 1. This is important. This is important stuff, guys. Define. We define variables. We declare variables. We say, hey, you know, one of the strongest, most powerful 3-letter words in the vocabulary is this: let. In mathematics, we have the power to let things be. We say, hey, you know what? Let X be the number of muffins bought. And call Y, naturally, the next letter after X is Y, the number of lattes bought. Do we know what they are? No. But X, yeah, we can also say X be the happiness. But let X be the number of muffins and Y be the number of lattes. This is the power of algebra. I don't know if I make this, if this is apparent enough. This is how powerful understanding what you don't know. So this is the unknown, right? X is unknown, Y is unknown. But we kind of say, I know what I don't know. I know that I don't know the number of muffins, and I know that I don't know the number of lattes. But that's okay. So step 2. Now we create the system. What's the system? Well, we know that whatever they are, X plus Y, so the sum of the number of muffins and the number of lattes, if you put them all together, they have to equal what? 7. Okay, and then that's the total number of items. And so then what is the total number of, what's the total cost? Well, if I have X muffins, how much am I actually paying for them? I'm paying 2X for the muffins, right? And then if I have Y number of lattes, for every latte, I'm paying $3. So in total, I'm gonna have 3Y. And the total amount is gonna be 18. So the first equation tells us the total number of items. And the second equation tells us the total cost. And you see that? This is a system now. I translated these words into variables and into equations, and therefore into a system of equations. And the nice thing is I know exactly how to solve. So solve the system. And how would you solve this system here? Would you use would you graph it? Would you use substitution method, or would you use elimination method? It's really, it comes to your preference. But we can just choose one. If nobody has any preference, we can just let's use substitution method. So solve by substitution. The reason why I use substitution is because it's very easy to do so, especially when we use the first equation, right? So I'm going to solve for X this time. I'm not going to do the Y. Solve for X first. So I'm going to say X plus Y equals 7. So X equals 7 minus Y, correct? So I got X equals 7 minus Y. And then I'm going to plug in this is equation 1. And then equation 2, I got 2 parentheses plus 3y equals 18. Why am I putting parentheses? Because I'm plugging in 7 minus y into X. Then I distribute the 2. I get 14 minus 2y plus 3y equals 18. Combine, I get 14 plus y equals 18. Subtract by 14, subtract by 14. I get that y equals 4. So I figured out what y equals. Now all I have to do is solve for X. And I can use the first equation because it's the easier equation to deal with. The first equation is X plus Y equals 7. So if it's 4, then what's going to be Y? Y will obviously be, pardon me. I replaced the Y, not the X. So it's going to be X plus 4 equals 7, and X must equal 3, right? So what did we just accomplish? We found out that there must have been 3. What does X represent? X represents the muffin. So there must have been 3 muffins and 4 lattes purchased at the store. And there's many other scenarios where systems of equations can be created and as a result solved. Okay? Any questions? Clear? Is it good? Do you see the power behind solving systems of equations? It's an extremely powerful tool, especially when we talk about higher, bigger systems, not just a 2x2 system. This is like the smallest kind. When you talk about bigger 3x3, 4x4, 10x10, it gets very, very useful. All right. Okay, so we'll stop here with